In this section, we want to know whether a data set is perfectly linear or not. There's a couple methods we can use for this. One involves just graphing the data set with technology. So I'm going to use the site desmos.com for this first example. And I'm going to enter my data into this table, and then we'll just look at the scatter plot that it creates, and we'll try to decide whether the data is linear or not. Okay, so here is a plot of our data, and just going by eye, it looks like it may fit a perfect line actually. In order to decide whether it really does fit a perfect line, we can use regression. So type in y1 tilde mx1 plus b. That's the general equation of a line. And as we can see, this data set actually is perfectly linear. The way we can tell is visually the points are actually on the line. Every point is on it. And also we see that the R correlation coefficient is 1. That means perfectly linear data. Now we're going to want to take our slope M and our intercept B that the program gave us, and we want to put that into a line equation which models this data. So go back to the program here. Our line equation will be of the form y equals mx plus b. Okay. This one was perfectly linear. Okay, we found that our m is 4 and our b is 0, therefore making our regression equation y equals 4x plus 0, and we can simplify that to just 4x. Now the hat on the y means that it's a regression equation formed from data. You could leave it off or put it in, either way. Okay, now what's the other method that I mentioned that we could use to decide whether it's linear or not? Well, if a data set is truly linear, then if we take any combination of points on the line and calculate a slope for them, then we should get the same slope no matter what points are chosen. So I'll just use the slope formula here. Oops. I'll make this point 1, and this can be point 2. Okay, so 20 minus 8 over 5 minus 2. Punch that into calculator. And it comes out 4. And that is supposed to match what our program had told us, if it's perfectly linear. Okay, now that's just one combination. We want to compare that with another combination, so I'm going to pick point 1 again. But this time I will pick point 4, let's say. Okay, we'll do the calculation again. y4 minus y1 over x x4 minus x1. You get 32 minus 8 over 8 minus 2. Okay, comes out to 4, which matches the slope of the line. See, they're actually all going to be 4s here, no matter what points you choose. Just to do one more, let's say I take point 3 and combine that with point 5. Okay. y5 minus y3 over x5 minus x3. 44 minus 28 over 11 minus 7. And it comes out to, once again, 4. Now you haven't really proven that it's linear until you get all combinations of the points. So that's why technology would be more helpful here. It'd be quicker, certainly. But if the data is nonlinear, then all we need is, if it's not a perfect line, we just need one of those slope calculations to be different. So let's see where that may happen in the next problem. Let's graph it in Desmos here first. Okay, those are our points. Here is the data. As you can see, this is not perfectly linear data. It is actually well modeled with a line equation, though. It's close to linear, but it's not perfect. The way we know it's not perfect is the dots aren't all on the line. There is no line that will go through all of them. And we can also see that our R correlation coefficient is not quite 1, but it is really high. It's 0.991, which is almost perfect, like almost a perfect line, but not quite. So let's prove by hand that it's not really linear. How do we do that? Well, use the same technique as above. Pick 2 data points to calculate your slope with. That slope comes out to 2. Okay, so it's a slope of 2 between those first 2 points. Okay, now we have to make another choice of points. Let's pick the first and the fourth. Okay, that comes out to 2 as well. Now let's do one more choice. The first with the third. Okay. Okay, this time I get 2.375. Okay, so since all the slopes do not match, this data is not perfectly linear.